Ion regulation is important for fish to live. But is it the same for the freshwater and marine water fish? Fish gills regulate ions differently in freshwater and seawater because the concentration of salts differ in freshwater and ocean water. Let's first talk about gills. Gills are breathing organs of the fish, just like the lungs in humans. It is a site where gas and ion exchange occur. The gills are also permeable to respiratory gases and ammonia waste products. The fish gulp water through their mouth and pump it over their gills. Most fish have 4 gill arches that run between the gill slits on each side of the head. Let's take a closer look at the gill structure. The inside of each gill consists of flesh-like thread-like filaments. These filaments are closely spaced along the gill arc in 2 rows. Water from the mouth then passes over these filaments. The primary lamella is a site where the chloride cells are located. This determines whether the fish belongs to the marine environment or a freshwater environment. Freshwater fish have more chloride cells than seawater fish in order to keep the sodium levels high. These fish are hypotonic to their surrounding, meaning that their blood has a higher water concentration than the surrounding seawater. As seawater passes through the mouth and over the gill membranes, water molecules diffuse out of the blood into the seawater by osmosis. The fish must replace the lost water by the process of osmosis. To replace the water they lose, saltwater fish drink seawater. Drinking seawater then brings a large quantity of salt into the blood, and this has to be removed. They also produce a very small volume of urine. Salt is removed by chloride secretory cells in the gills, which actively transport salt from the blood into the surrounding water. In the ocean, the sodium and chloride ATPase molecules pump sodium and chloride out of the fish blood into the salt water flowing over their gills. So let's take a closer look at the ion exchange mechanism in the gills.
The Na+2Cl-K+ cotransporter brings the Cl- and K+ into the cell using the Na+ electrochemical gradient. K+ and Na+ separate from the 2Cl-. 2Cl- then separate and exit the cell through chloride channel down its electrochemical gradient to the seawater. K+ exits the cell through the K+ channel back to the extracellular fluid. The Na+ that entered through the Na+2Cl-K+ cotransporter leaves in exchange for K+ via their Na+K+ ATPase. At the same time, some Na+ move to the seawater through electrochemical gradient. In freshwater fish, water intake happens along food intake. The water is also absorbed through gills and skin by simple passive diffusion. Because of the continued diffusion of water by osmosis into the fish, sodium and chloride ions also diffuse out of the fish down their concentration gradient. Special cells in the gill lamellae contain sodium and chloride pumps. There are special enzymes to move the ions up their concentration gradient by ATP to maintain their higher concentration in the fish. The fish also produce a lot of dilute urine. Let's take a closer look at the ion exchange mechanism in freshwater fish. The mechanism of Na+ uptake and Cl uptake are independent and different. From dilute pond water into concentrated blood, Na+ is transported by active transport against the concentration gradient. It simultaneously secretes H+ into the water in exchange for Na+. The chloride pumping mechanism secretes bicarbonate ions in exchange for Cl-. Both H+ and HCO3- metabolic waste are derived from CO2 produced by metabolism. The H+ and HCO3 keep it from generating large charge difference across the gill epithelium in freshwater fish. A protein that is involved in sodium uptake uses ATP to exchange incoming sodium ions for potassium ions. Here is an overview of how saltwater fish regulate their ions. And here is an example of how freshwater fish regulate their ions.